moving forward in stoichiometry, we need to take a look at our moles when we're interpreting our equation. We know that we can interpret it for molecules and mass and several other things, but I'd mentioned that moles would be the most important. So we're going to look at this mole ratio. This is a conversion factor, and it comes from the coefficients from that balanced equation. Again, I can't tell you how important it is you have a balanced equation. That's what you need to look for first. Your mole ratios are a way for you to convert between substances. So if you want to convert between the reactants side to how much product you're going to make, you need a way to convert between one substance to another, and that's going to be your mole ratio. So if we look at this balanced equation, we can we can make three mole ratios from this. We can say that we have a mole of nitrogen for every 3 moles of hydrogen. We can say that we have a mole of nitrogen for every 2 moles of ammonia. Or we can say we have 3 moles of hydrogen for every 2 moles of ammonia. And then, to be honest, we could actually make 6, because each of these can also be flip-flopped or inverted, and we could get, the opposite. So you can have 6 different conversion factors just from this one balanced chemical reaction, but again, you have to have a balanced equation. Absolute must. Now we're going to do a few practice problems together, and in this first one we are still in this one going to be using the balanced equation from the previous slide, but just so that I can see it as I'm working, we're going to rewrite it. You don't have to, though. Alright, so here is our balanced equation, because we have to start with a balanced equation, and now it wants to know how many moles of ammonia, okay, ammonia is NH3, how many moles of ammonia are produced when we start with the 0.60 moles of nitrogen. So we know that we have 0.60 moles of nitrogen, and we want to get rid of moles of nitrogen. We want the moles of nitrogen to go away. What we're asked for is moles of ammonia. Now, in the previous unit, when we did converting from moles to grams and molecules, we didn't switch to a new substance. We stayed within just the one substance. Well, now we need to be able to convert between reactants and products, or products to reactants. And so in this case, we have to use a mole to mole ratio to go from one substance to a new substance. That's the only way you can do it. We do know that we want moles of nitrogen to go away, so we would start with at least being able to cancel out units. Alright, so that's a good place to always start. Whatever you're trying to canceling, put it on the bottom. And now we don't want grams of N2, we don't want molecules of N2, we want to switch to ammonia. And the only way that we can convert and have a whole new substance is a mole to mole ratio. So we're going to put moles of ammonia on the top. Now this is where interpreting our balanced equation will come in handy, because we know that the coefficients that are out front represent moles. So how many moles of N2 are there? In our balanced equation, it only shows 1. There's 1 mole of N2. But moles of ammonia, there are 2. So we need to have 2 moles of ammonia for every 1 mole of N2. That's just one conversion that we can make, and that's actually one of the conversions that was on the previous slide. So now, with the moles of nitrogen gone and the moles of ammonia is what we have and what we want, then we can multiply the 0.60 times 2, and only keeping 2 significant digits anyway, 1.2 moles of NH3. So to go from moles of one item to moles of another item, you have to use the mole to mole ratio, and it's just a one-step conversion problem. So let's switch now to a new balanced equation. This is balanced, so we're starting off good, and we want to know how many moles of aluminum are needed to form 3.7 moles of our aluminum oxide. So moles of aluminum is our question mark. We don't know how many of those we need, but we do know that we're starting with 3.7 moles of our aluminum oxide, and we don't want moles of aluminum oxide, so we are going to put that on the bottom so it will cancel, and instead we want to go to a new substance, and to be able to convert from aluminum oxide to aluminum we need to do a mole to mole ratio. So moles of aluminum, and that is 2 moles of aluminum oxide, and we get 4 moles of our aluminum from our balanced equation. These numbers always come from your balanced equation. If your balanced equation, well, if it's not balanced, then you're going to have incorrect answers when you're doing this. So for this one, we need to take 3.7 and multiply it by 4 and divide it by 2. And when we do that, and we only are using 2 significant digits, we get 7.4 moles of aluminum. So there's your amount there. And then this last one I am going to let you do. Now for this one, the balanced chemical equation is on the previous problem, practice problem number 2. So I will go ahead and rewrite it just so that you know for sure that it is balanced. And you're going to be doing very similar to what we did in practice problem number 2. The only thing is that we are starting with moles of aluminum. That's what you're going to be starting with over here. And we want to convert it to moles of oxygen. It doesn't matter if they're both on the reactant side. It doesn't matter if one's on the reactants and one's on the products. You can still make mole to mole ratios as long as it's a balanced chemical equation. So we want to convert our moles of aluminum to the moles of oxygen, and make sure that your answer has 3 significant digits in it, and I will be checking that the next time I see you in class. If you have any questions, by all means, let me know.